Hello everybody. In this video, we are going to talk about two concepts, differentials and linear approximations. They're actually motivated from one application. And this is still partly from section 14.6. So first we recall the tangent plane to a surface. So in the previous section, we had talked about a surface given a surface in 3D space. So in other words, it could be f x y z equals c is some constant. Maybe we can just do this here, 0. Then, and your standing, the current position is, suppose p is x0, y0, z0. So you're standing on this coordinate in the 3D space, which is on the surface. Then what is the tangent plane? Going through this point, then the solution is, the formula we have done is, it is this is the formula for the tangent plane, or you can write this as, so from inner product of two dot product, you can write this as fx. Maybe we can just easily write this, for briefly write this in p0 times x minus x0 plus fy p0 y minus y0 fz p0 and z minus z0, z minus z0 equals 0. That's the equivalent way we write. And now this is called implicit function, which serves for 3D surface. Now if I give a implicit, so this is implicit. Now if I give explicit surface, then what is the tangent plane? Actually, this explicit function is one of the special case of the implicit function. So we can, so for explicit surface, if I give that z equals f of xy, then you can always write this into implicit form. Then this is the same as fxy minus z equals 0. Then we can use this formula applying to this function. In other words, this is corresponding to the whole function to the left hand side, and we take the derivative of partial derivative of f with respect to each variable and take the dot product. That's what we do. So it is, if I take partial derivative of this with respect to x, then it's the same thing as taking derivative of f of xy, because z is nothing to do with x. And then x minus x0. The same reason we do fy p0, y minus y0. Now if I take the derivative with respect to z here, then there's nothing related to z, so z derivative is 0, and negative z means negative 1 after derivative. So negative 1 times z minus z0 equals 0. This is exactly the tangent plane for a surface given in explicit form. So we can look at here the tangent plane to a surface given by z equals f of xy at the point x0, y0, f x0, y0. This is z0, right? So the height of this mountain. Then the formula is given like this. All right. Now linearization. So the point is how to approximate f of xy using linearization. So what it means is that sometimes f of xy is not easy to, it's given by very complex function which is hard for evaluation. Then I want to linearize. In other words, I have some substitution for f of xy, which is we call lxy, but the value, of course they are not equal, but the value are close enough to original f of xy. So it becomes an approximation. So what kind of situation makes it close enough? So suppose you can think of the 3D surface is something like, the picture is not very clear, you can imagine, but suppose this is the surface and you're standing at some point here, right? And I'm interested in the values at the neighborhood close enough to this point near your position, but the function is hard to evaluate. Then what you do is I will put a glass board to maybe I will put a glass board across on top of this surface, which is just touching it at that point. Then at this at neighborhood of your position, the glass board has not the same height, but approximate close enough value to the real surface. That's what linearization means. Linearization means, so glass board is linear function, and that's why we do linearization approximation. So what is Lxy? Or in other words, what is this glass board? The glass board is tangent plane at this point. So Lxy is going to be equals your original position f of x is 0, y 0, plus the change in due to x and the change in due to y, so this and this. So this gives linearization. Or you can write this as Lxy equals f p0 plus, suppose I say this is p0, right? Plus gradient f p0 times x minus x0, y minus y0. So this is the same thing. And we have, so if you're talking about, if you're looking for the values close to your current position or neighborhood, then we can always have approximation. All right, so find the linearization of this. So we're looking your current position 3, 2, which is here, right? And I want 3, 2, 8. So 3, 2 is xy, and corresponding z is, if we put 3, 2 here, then you can see that 3 times 2 plus 1/2 times 2 squared plus 3, which is 8. So your this is z value is 8. We can directly do the algebra to get this. So your current position together with tangent plane gives your linearization. So we are going to do linear approximation of f of xy. So what we do is f, not f, but yeah, we can write f x xy, which is approximate, not equal, error xy, which is its linearization, which is originally I am standing at the current position and I change along the glass bond, which is fx p0 times x minus x0, and in y direction the change, corresponding change is this, and you need to add them up to get the total change, and we know that fp0 is going to be 8, fxp0, so take x derivative, then we get 2x minus y, and the last two values are y terms, so it becomes 0, and you to put 3 2 here, and x minus x0, and then we get y value, partial derivative of y, which is first term is 0, second term is negative x plus y 3 2, and y minus y0, and just plug in. So if I put 3 2, then 6 minus 2, which is 4, and x0 is going to be 3 plus, and 3 2 here, negative 3 plus 2, negative 1, y minus y0 takes 2 as its value, so this is, if I rearrange, 4x and negative 1y, and the rest of thing you can combine, 8 minus 12, which is negative 4, plus 2, which is negative 2. So this is approximation, which is error xy. All right. Now differential, it's more like mathematical terminology and symbols which will be used extensively in multivariable calculus and advanced analysis. So when we look at the change of f approximately, we linearize that. And the linearizing counts the sum of changes in different directions, in x direction and y direction. So we call the difference in f due to dx dy's, the sum of dx dy's, as total differential. So formally we write df. This is rigorous math notation, but we're not getting into very detail. So differential basically written as dx, differential of x is dx, differential of y is dy, and differential of f, or total differential of f, is df. Then the relation is df is equals rate of change in x and times the amount of change in the x. So this is the total change in x direction, and this is total change in y direction. This is called total differential, and we always have similar approximation. So we write change in f. So differential is like limit concept. So when it is getting smaller, dx, x change and y change is getting smaller and smaller, going to 0, then we write d instead of delta. But delta is the actual change we are looking for, even it is tiny. So this is approximately, we can write fx x0 y0 and delta x plus fy x0 y0 and delta y. So this formula actually implies an approximation. So the approximation says if you want to know the change in f, total change in f, the function value, then you need to count, you need to take the sum of x change and y change. But how do you find x change? Find the change rate in x and multiply by change in x. And change, this is ratio of change in y direction multiplied by y change. And then take the sum. All right, so we had total differential. We are going to use that. So here's this problem from geometry, 3D geometry. So cylindrical can, which is designed to have a radius 1 and height of 5. So it's going to be something like this. And this is R, and this is H. And we want to get R equals 1, H equals 5. But the radius and height are off by the amounts of this and this. So when this is designed to be like this, but actual manufacturing has some errors, and this is 0.03 error and negative 0.1 error in R and H. Then what is the actual, or what estimate the resulting absolute change in the volume of the can? So the can, we can write the volume of the can in terms of R and H. So pi r squared gives you the bottom area, and you need to multiply by H. That gives you the volume. So now we can think of F in the formula. So V is a function, pi is a constant, V is a function depending on R and H. So it's a two-variable function. But we can immediately think of this is a kind of surface in 3D, and total differential of d, not F, but dV is going to be VR. So this is rate of change due to R change, and then multiply by its change in R, and VH dH. This is another change due to the change of H. Now, what is delta V? Estimate. So we change all these by delta, but then we want to write equal sign by approximate the equal sign. And then VR, what is VR? VR is partial derivative of this with respect to R, so 2 pi RH, and R equals 1 and H equals 5 times delta R. Here delta R is gonna be 0.03. So maybe I can write this in the next line. Plus VH, take derivative of, with respect to H, then it becomes pi R squared, 1, 5, and delta H. And then we get 2 times pi times 1 times 5 times delta R is 0.03. Here they use dr, but this is the sometimes they can use that. So it's just the matter of notation. And R squared is 1 squared. So if we compute, oh, sorry. So there, yes, I forgot to write delta H, which is negative 0.1. So eventually we get, this is 0.3 pi minus 0.1 pi, which is 0.2 pi. The question is absolute change in volume. So if you get, in case you get negative number here, then you should take the absolute value to get absolute change. Now we talk about, now we already, so we find the linearization of two variable function. Then it says it is Lxy equals, or you can write differentials. That is easier than fx, x minus x0, fy, y minus y0. Now, if you have three-dimensional function, then its linearization is x change, y change, z change. Because there's another z direction, we have to count it into the total differential. And of course, the linear approximation of f, which is written as L, linearization, is this is total change plus existing value. So that's the way to linearize multiple variable functions. And that's pretty much all, and we're going to stop here.